Hello, this is the second part of talking about preparations of alkynes. I'm calling it part B. The second way of making alkynes is from alkenes. In the first part, we saw that you can make alkynes from smaller alkynes. In this case, we're going to see that you can make an alkyne from an alkene, essentially turn a double bond into a triple bond. We're going to take off those two hydrogens and make the double bond into a triple bond. But unfortunately, you can't take the two hydrogens off directly. They have to go through some other stuff first. So that's what we'll be learning today. Please read pages 260 to 262. It covers all the ways of making alkynes. So as I said in the first video, there are two ways of making alkynes. One is from terminal alkynes by adding another group on the end. So take the hydrogen off the end of a terminal alkyne, make it into an acetylide, and then add an alkyl halide, which adds the alkyl group onto the end of the triple bond. That was the other video. The second way of doing it is what we'll be talking about today, and that's from alkenes. So as I said a minute ago, you take an alkene with two hydrogens, and you turn it into a triple bond by essentially getting rid of those two hydrogens. So let's take a look at the overall process going from an alkene to an alkyne using a three-dimensional model in this case. And again, I'm not showing you the details just yet, but I'm just showing you the overall process. So we have two hydrogens here. They happen to be cis. It would work just as well if they were trans. And the overall process is we're going to take the two carbons. Obviously, you have to have two hydrogens. We're going to take the double bond and turn it into a triple bond. So it's as if we're taking off hydrogen and taking off the other hydrogen and making a triple bond. And there we go. It'd be nice if you could just kind of reach in there and pluck those two hydrogens off, but you can't. So here's what we have to do. It's kind of a roundabout way of doing it, and it's actually very interesting because although the ultimate goal is to take a double bond and turn it into a triple bond, what you actually do first is take the double bond and turn it into a single bond by adding bromines across that double bond. And that's a reaction that you're familiar with. You just add two bromines to a double bond. We learned that back in the alkene chapter. And then what we're going to do is a new reaction. We're going to add this material sodium amide, which you remember is a strong base. And we actually used it in the first reaction in which we make alkynes from terminal alkynes because it's a strong enough base that it can pull hydrogen off the end of a triple bond. Interestingly enough, and totally coincidentally, it's also a strong enough base that it can pull off a hydrogen of this type right here. And so that's what it does. It pulls off a hydrogen and kicks out the bromine next door. And then another equivalent comes in and takes off the other hydrogen and kicks off the other bromine next door. And so we ultimately go bink, bink, and make a single bond into a triple bond by adding two equivalents of sodium amide. But that only works if the chain continues on both ends of the double bond. If the double bond ends a chain, so we might call it a terminal alkyne, first thing we do is the same. We add two bromines across the double bond and it makes it into a dibromide. And then we're going to add not two, but three equivalents of sodium amide. The first one's going to take off a hydrogen and kick out a bromine. The second one's going to take off the other hydrogen and kick out a bromine. And that would get us to the triple bond, as it did here. But then that has a hydrogen on the end of it. Remember what sodium amide does with a hydrogen on the end of a triple bond? It pulls it off. And so you make an acetylide. And so you put three equivalents in. One takes off a hydrogen and a bromine. The second one takes off another hydrogen and another bromine. Third one takes off the hydrogen from the end, and you make an acetylide. And then, we don't really want an acetylide. What we want is an alkyne, and so we add water, just plain old water. It's a strong enough acid that it protonates the acetylide, which you remember is a very, very strong base. Water is a good enough acid to do that, and obviously cheap and not toxic. And so it then adds the hydrogen back on. So essentially, the third equivalent of sodium amide pulls off the H+, and then the water adds it back on again. Now, you may wonder, couldn't we get away with just putting in two equivalents of sodium amide and not pull off that hydrogen on the end and go directly to this instead of having to go to this and then back to this? And the answer is, unfortunately, that doesn't work because it starts pulling off that H+ from the end even before all the rest of the molecule turns into the alkyne in the first place. And so you end up with a big mess. So we have to essentially let it happen, go all the way to the acetylide, and then put in water to put the H+ back on the end. So these are essentially two slightly different variations on the same reaction. One if the double bond is in the middle of a chain, one is if the double bond is at the end of a chain. Let's consider this set of reactions in sequence. First reaction, the first part of the whole sequence is adding bromine across the double bond. As I said, it's an anti-addition. You're very familiar with that reaction. You know the mechanism of it, although we won't go into it now because we covered all that in a previous chapter. But let's go and look at the second reaction. This is what I'm referring to as a double dehydrohalogenation. So let's analyze this long name here. Well, first of all, you remember that when you have an alkene and you add hydrogen to one carbon and bromine to the other, that's called a hydrohalogenation. If you take off a hydrogen and take off a halogen, then it's called a dehydrohalogenation. And we'll be learning more about dehydrohalogenations in a future chapter, but for now just remember that it means taking off a hydrogen and a halogen, so dehydrohalogenation. And then it turns out we're going to do that twice, and so it's a double dehydrohalogenation. So we take off a hydrogen and a bromine to dehydrohalogenate it once, and then we take off another hydrogen and another bromine to dehydrohalogenate it again. So it's a double dehydrohalogenation, and that's why you need 2 equivalents of sodium amide to do it. So that's a little bit complicated reaction. Let's do a couple things. Let's start with the balance equation. So here's the equation. Starting with the dihalide, we add in 2 equivalents of sodium amide. We end up with the alkyne, so both hydrogens and both bromines are now gone. We have the triple bond there instead. The NH2 negative from the sodium amide pulls out a hydrogen, so it becomes ammonia. That happens twice, and so it becomes 2 ammonias. And then the sodium ion that's left and the 2 bromines become bromide ions, and so you end up with 2 equivalents of sodium bromide. We'll go through the details of how that happens when we do the mechanism here in a minute, but what I want you to see is that the balance equation is only a little bit tricky. You know that you're going to take your dihalide, you know you're going to add 2 equivalents of sodium amide, you know you're going to get an alkyne, and then the other things that are left over are 2 ammonias, which by the way is a gas and disappears out of the reaction mixture, which makes it a lot simpler. And then the other byproduct is just sodium bromide. That's an inorganic ionic compound. Typically it'll just crystallize out of the reaction mixture and you just filter it out and you're done. So the work up here is actually pretty easy. Now let's talk about the mechanism. So I've rewritten the balance equation here. So again, this is just like what was on the previous slide. Here's what happens. So I've drawn curved arrows, I've balanced everything out, shown exactly where bonds break and so on. So here comes the NH2 negative. This is its Lewis dot structure. One of these pairs of electrons comes in and grabs off that hydrogen. So basically it's acting like a base. It's pulling off that hydrogen, putting in a pair of electrons there to form a new bond with the hydrogen. That drops this pair of electrons in to the middle to form the double bond, and that kicks out the bromide from the other side. So ammonia forms, bromide forms, and a double bond forms. So at that point you actually have gone from a single bond back to a double bond. But that's not the end of it, because it happens a second time. So here's the second equivalent of amide. It comes in, pulls off the other hydrogen, drops it in to what is now the double bond, making it into a triple bond, and kicking out the bromide. So it becomes Br negative. So it's essentially the same mechanism twice. It's a one-step mechanism. Ammonia forms, drops a pair of electrons in, kicks out bromide, and then the exact same mechanism happens again. Ammonia forms, drops in a pair of electrons, and kicks out bromide. So it's basically just bing, bing, and then bing, bing, and you're done. So it's a 2-step mechanism. Actually, it's the same reaction happening twice. So 2 different 1-step mechanisms. So now that we know the balance equation and we know the mechanism of the double dehydration part, let's go ahead and predict some products. So this one is easy. If you started with this alkene and added Br2 to it, what would you get? Well, this is old review of alkene chemistry, so you should be able to do that real quick. So write down the product there. And there it is. We're just going to add 2 bromines across a double bond. I drew one up and one down just because it's more convenient on a stick figure to do it that way, but it really doesn't matter what the stereochemistry is. Then we're going to add the 2 equivalents of sodium amide. So go ahead and draw the product of that reaction. It's not too bad. You know you're going to take off a bromine and a hydrogen, and then another bromine and another hydrogen. The only tricky thing is, in a stick figure like this, you don't see the hydrogens, but don't forget there's one there on that carbon, and there's one there on that carbon. So go ahead and stop the video, draw the product, and then come on back, and I'll move to the next slide. Now, okay, so here's the product. Notice that this is probably the easiest one. I've drawn it 4 times, but it's really all the same thing, just in different notation. So what I did was I essentially just took this structure right here, removed a bromine and a hydrogen, put in a double bond, so that would be here. Then I removed another bromine and another hydrogen and put in a triple bond, so that would be that one there. We're looking at it from the very beginning. Essentially, you're just taking that double bond and making it into a triple bond. So there's your product. The only thing I don't like about this particular kind of structure is it sort of implies that these are angles in here, whereas in fact we know, because it's an alkyne, it's actually sp hybridized on both carbons, so it's actually straight across. It's a little bit more realistic picture in terms of shape, but it's a little trickier because you don't see angles here. But you do realize that there's a carbon at that position and a carbon at that position. just like I've drawn here. I just kind of drew in the carbons explicitly. And then in this one, I just went ahead and drew in the CH3, CH2, CHs, and so on. And so this is the same as that, which is the same as that, which is the same as that. Just drawn in different formats. Okay, so now I want you to give the product. If you were to take this alkene, and this is an interesting one because it has 2 benzene rings on it. This is a compound called trans stibene, and we have some in our stockroom. And we could do this experiment and see what happens, but I've never actually tried it. So if you add bromine first, and then add 2 equivalents of sodium amide. Now in this case, I put them both together on the same arrow instead of 2 different arrows, but it means the same thing as long as you put the number 1 and the number 2 there. So stop the video, go ahead and draw the structure of the product that you would get after doing both steps. And we'll be right back in a minute and I'll show you what you get. There you go. So the double bond becomes a triple bond. So hydrogen here is gone, and hydrogen here is gone, and we made the double bond into a triple bond. Of course, in the process, when we first added the bromine, the double bond became a single bond with 2 bromines attached, one up and one down, and then the sodium amide took off 1 hydrogen and 1 bromine, and another hydrogen and another bromine, and made it into a triple bond. So again, this is actually a really simple thing. If you just remember the reagent, all you do is you take the double bond and you turn it into a triple bond. Now the thing you got to remember though is it only works if you have hydrogens at those 2 positions. Now, remember I talked about a special case? If the alkene is terminal, meaning it's at the end of a chain, so it stops with a CH2 and there's no other carbons attached on one of the alkene carbons, then here's what happens. First thing you add the bromine, and that adds across the double bond just like you'd expect. That's not different. But then we're going to add 3 equivalents of sodium amide, not 2. Remember the first one takes off a hydrogen and a bromine, puts in a double bond. The second one takes off another hydrogen and another bromine, puts in a triple bond. There would still be hydrogen on there. And then the third one takes off a hydrogen and turns that into an acetylide. So this, again, is an acetylide ion. Then at that point, what could happen? If you have an acetylide ion, you actually know of 2 things that could happen. One thing that I mentioned earlier is you can just add water to it, and adding water adds a hydrogen on there, and you end up with an alkyne. So that's what we've been talking about to this point, where you can take an alkene and turn it into an alkyne, essentially just remove hydrogens from those 2 positions. After having gone through the process, you end up with an alkyne. So terminal alkene becomes a terminal alkyne. Or, interestingly enough, what else can acetylides do? Well, we learned in the previous video that acetylides can react with alkyl halides in what's called an alkylation of acetylides and stick another R group on there. So that's what happens. If you add, instead of adding water at this point, if you add an alkyl halide, it sticks an R group on. And so you can literally combine the 2 reactions. You can take an alkene, turn it into an acetylide, and then acetylate it and turn it into a longer alkyne. That would be, of course, a carbon-carbon bond-making reaction right there. Now remember, it only works if this R prime is methyl. So if this is methyl chloride or methyl bromide, or primary, like ethyl or N-propyl or something like that. If it's secondary or tertiary, the reaction doesn't work. It gives you other products. Okay, so here's some examples of the special case. So here is a terminal alkene. It's at the end of the chain. If we first add bromine, and then 3 equivalents of sodium amide, and then water, what would the product be at that point? Here's another example of a terminal alkene. If we had bromine and then sodium amide, 3 equivalents. And by the way, you can just put excess in here, so little x, little s to stand for excess, and that is just fine as well if you want to note it that way. But then we add water, so what would the products be at that point? Go ahead and draw them out. So essentially, this double bond becomes a triple bond. This double bond becomes a triple bond. In this case, I put in the 2 carbons and hydrogen explicitly, so you can see that that double bond became a carbon-carbon triple bond. This carbon became that carbon, and this carbon became that carbon. So you should have something that looks like these 2 products written down. Now, we're going to talk a little bit about synthesis problems here, as we did in the previous video. In other words, you need to be able to look at a product or look at a molecule and say, how could I make that molecule using these reactions that I'm just learning? In other words, when you learn a reaction, you learn it forwards, but you also have to learn it backwards, meaning if I wanted to make this, what reagents would I use? So I want you to stop the video and give me an organic starting material and 1 or more reagents to make this right here. In other words, draw something over here, draw an arrow, and put something over or under or both on the arrow. So here are the 2 ways that we talked about. If you add bromine and 2 sodium amides, would that work in this case? No, because this is a terminal alkene. In other words, there's no other carbons on this carbon, so it's not going to work. So let's X that one out, and instead we need to do this one where we add bromine, and then 3 equivalents of sodium amide, and then water, and that would then get you to this terminal alkyne. And that's the end of that video. Thank you for your attention.